Okay, so let's take a look at number 9. A medical researcher says that less than 25% of U.S. adults are smokers. In a random sample of 200 U.S. adults, 19.3% say that they are smokers. At alpha equal 0.05, is there enough evidence to support the researcher's claim? Okay, so if this were all mixed up on a test, the first thing you want to identify is what parameter are we testing? Okay, because the claim is about a percent or a proportion, this would be a hypothesis test about P. Okay? So the first thing I'm going to do is write that claim in terms of the parameter. Okay, so the researcher says that less than 25%. Does that include the 25%? No. So the claim is P is less than 0.25. Okay, so that would be the researcher's claim. Is this the null or the alternative? This is the alternative. Okay. So this makes the null P greater than or equal to 0.25. Okay. So this is going to be a lower tail test. Now let's real quick check to make sure that we can use the z-test. So we want to know, is n times p at least 5 and n times q at least 5? Because I do ask for this on your lab. But in the homework, you probably won't have to do this step. Okay, maybe just a few at the beginning of the homework set. Okay, so in the problem, we're given that n is equal to 200, and p hat, the sample proportion, was 0.193, right? 19.3%. Okay, so the question right here is 200 times 0.193 at least 5? Okay, so let me get that actual value. Okay, so 200 times 0.193. Okay, so yes, this is about 38.6. It's greater than or equal to 5. Okay, and we need to check n times q. So 200. Okay, so q is 1 minus p. Okay, so that's going to be 1 minus 0.193. Is that at least 5? Okay, so that value is 161.4. Okay, that's greater than or equal to 5, so yes. Okay, so we can use the z-test here. Now, we're not using the z-test, that first option in the calculator. Again, we're using the one proportion z-test. This just gives us the justification to go ahead and use the z-distribution, okay, for the test statistic and the critical value. Okay, so let's go ahead and find the standardized test statistic. Remember, it's p hat minus p over the square root of p times q over n. So plugging into this formula, I have 0.193 minus 0.25 over the square root of 0.25. Okay, I made a mistake up here. Someone should have caught me. What was I testing? Whether n times p is at least 5? Okay, and I used what here? I used p hat. Okay, this is what we had to do for the confidence interval. Okay, so real quick, sorry about that. This should be instead, let me go down here. You guys are supposed to be the wind beneath my wings. Why didn't you?
Chocolate.
It's the chocolate. It can be confusing because this is what we have to do to check the assumption for the confidence interval. Because we're not making any assumption about P when we're in chapter 6. Here we assume that P is true, okay, until proven otherwise. Okay, so it's a slight difference. Okay, so, oops, right, let me go back. Okay, so I'm going to check 0.25 here. Is that at least 5? And 200 times 0.75. Is that at least 5? Okay, so what is 25% of 200? 50. Okay, so yes, that checks. And what's 75% of 200? 150. So yes, we can use that. Okay, sorry about that. I make that mistake all the time. Okay, because this is one slight difference between the confidence interval and the hypothesis test in checking that assumption. But for hypothesis test, we use P and Q, not P hat and Q hat to check that assumption. Okay, shoo. All right, so going back to the test statistic, in this denominator, I have 0.25 times 0.75 over 200. Okay, again, I know it's kind of cumbersome to input into the calculator, so I'm going to go ahead and use parentheses to around the numerator. Whoops. So 0.193 minus 0.25 divided by the square root of 0.25 times 0.75 divided by 200. That whole thing is in under the radical, also known as the radicand. I love that word. It sounds exciting. You remember that from algebra? The value under the radical is the radicand? It's a good word. That and trapezoid. I like those words. Okay, so do you guys get negative 1.86? Okay. Okay, so now I need to find the critical value. Okay, so critical value, look, I'm getting lazy, I'm not even writing it out. Okay, so using, what's my level of significance in this problem? 0.05. Okay. It's a lower tail test. I know that by looking at the alternative. Okay, so I'm going to shade a lower tail down here and indicate an area of 0.05. Okay, because I'm using the z-distribution, I could go ahead and use inverse norm and put in a cumulative area of 0.05. Okay? Or read in the body of the table to get as close to 0.05 as possible, and then read outward to find that z-score. Okay, so I'm going to go to my distribution, select inverse norm. Okay, so do you get negative 1.645? Yes, it's a common one. All right, so now we have enough information to make a decision. Where does our test statistic lie with respect to that? Here's our standardized test statistic. It's in the rejection region, right? It's below negative 1.645. So my test statistic is way down here. And then I'm going to find the corresponding p-value. Okay, that would be that little bitty area in the tail. Okay, so right now I know I'm rejecting the null hypothesis. Okay, so if I'm going to reject the null hypothesis, am I supporting the researcher's claim? Yes. You said that with confidence too. Because I'm rejecting the null, in this case I'm supporting the researcher's claim. Now remember, the claim can be either one. So there's two parts to our decision. We're going to either reject or fail to reject the null, and then we need to decide whether or not the claim is supported after that. Okay. Okay, so we know our decision is to reject the null and support the claim. Let's go ahead and find the p-value. Okay, so I'm going to use the calculator to find the p-value. If I wanted to, I could do this by hand. It would be the probability of getting a z-score less than negative 1.86. I do not have to double that because it's a one-tailed test. Okay? So if you wanted to do that by hand, you would use the normal CDF, okay, because you're given the z-score and you want to find that corresponding area. Okay, but instead I'm going to go ahead and use the calculator. I'm going to use the one proportion z-test. Okay, so I'm going to go to Stat, right arrow over to Tests, and scroll down to one proportion z-test. Okay, we will double the fun in Chapter 8 and do the two proportion z-test. I know you can't wait. Okay, so I need to change the values here. My claimed proportion was 0.25. Okay, now I need to get x and n. Okay, now the problem gave the information in terms of the sample proportion. Okay, so remember p hat is x over n. P hat was given to be 0.193 or 19.3%. Okay, so x over 200. So x is going to be equal to 0.193 times 200. Okay, so in other words, I need the number of successes out of 200 to get that in the calculator. So 0.193 times 200 is 38.6. Okay, now the calculator's not going to like that. Okay, it's going to be expecting a whole number. So let's go ahead and round that to 39. Now what's interesting is StatCrunch will let you put in 38.6. So StatCrunch's output will be slightly different than the calculators. So when you try this in StatCrunch under Stat, then Proportion Stats, you can go ahead and put in a decimal value for the successes, but not in the calculator. All right. Okay, so going back to the calculator, going back to my one proportion z-test, my number of successes is about 39 out of 200. And then I want to change my alternative to be less than. Okay, so look at the z value. It's negative 1.796. And what did we get by hand? Negative 1.86. Now, out of curiosity, I'm going to go ahead and change that x value to 38 and see if that gets closer to that test statistic by hand. Unfortunately, the book doesn't really give any good rounding information. Okay. Essentially, we want to choose an x value that gives us as close to 0.193 as possible. Okay, so let me go back there and change that to 38. Okay, that's even, is that worse than before? Yeah, Is it better? So a problem like this, I would go ahead and stick with 39. And in your lab, I'll go ahead, if this becomes an issue where it doesn't come out to be a whole number like that, I can't remember what your lab problem is for proportion. Okay, I'll go ahead and do it both ways with you rounding up or rounding down. Okay, and I'll accept both of them. In StatCrunch, you can put in that fractional value. So in StatCrunch, you should be able to get as close to the exact answer as possible. So keep that in mind when you're doing your homework. Okay, maybe a better option if you don't get a whole number for your number of successes to go ahead and do it in StatCrunch. Okay, so suggestion. Okay, so
so there's not a way to get the critical value with the calculator?
Yes, there is a way to get the critical value with the calculator. I'll do that here in just a second. Okay, so let me finish this. So one proportion z-test. I'm going to go ahead and change that back to 39. Okay, so the standardized test statistic using the calculator is about negative 1.80. Okay, and when we did this by hand, we got a standardized test statistic of about negative 1.9. Okay, remember it was negative 1.86. Okay, all right, but if we look at both of these test statistics and compare them to the critical value, what is our decision? Still, we're rejecting the null. Okay, if we put in 38 for the number of successes or 39 for the number of successes, we're still getting the same conclusion. Again, for a problem like this, I'd probably turn around and do this in StatCrunch because I can put in that decimal. Okay, so I'm going to reject the null and conclude that the claim is supported, and I, again, would write that out in plain English. I'm running a little bit out of time here, so I'll leave that part to you. Okay, since we rejected the null, it is possible that a type 1 error may have occurred. Okay, it doesn't mean that it did. It just means that it's a possibility. Okay, remember you can't get a type 1 or a type 2 error at the same time because you can't reject or fail to reject the null at the same time. Okay, so the question is getting the critical value from the calculator. Okay, so let me go back and do that part. Okay, oops, not the p-value, the critical value. Either I stop eating chocolate or eat more chocolate, so I'm always in that frame of mind. Okay, sorry. So the critical value using the calculator. Okay, so what was our level of significance? 0.05, right? And it was a lower tail test. So I want 0.05 area in this lower tail. So it's a problem where I'm given the area and I'm working backwards to find the z-value. So I'm going to use my inverse norm by going to distribution and inverse norm. I put in a cumulative area. So since this is a lower tail test, I can leave it as 0.05. Okay, so see that I got negative 1.645. Did that help? Yeah, okay. Good. Okay, and then again, I would be writing my conclusion out in plain English. To get the corresponding confidence interval, real quick, that's also under stats and then tests. It's the 1 proportion z interval, so I have to scroll down a little bit. Okay, and it should carry over the information. I'm going to change that to 38. And since my level of significance was 0.05, I have a 95% confidence interval. Okay, so the confidence interval goes from 0.1356 up to 0.24. Okay, and our null in this case was that p was greater than or equal to 0.25. But remember, we were in favor of the alternative. So does this confidence interval support that decision? Is the confidence interval, all of it below 0.25? Yes. Okay, so that's supporting this alternative. Okay, p is less than 0.25. This confidence interval is entirely below 0.25. So that would be consistent with rejecting the null. Okay?
So if the p-value by hand is a lot different than the one we got on the calculator, should we just do that on StatCrunch too?
Yes. You know, either way, the p-value is going to be less than 0.05. Okay, what would be different is by hand, we would be finding z less than negative 1.86. By hand, we'd be finding z less than negative 1.8. So, you know what, I would go off the p-value from StatCrunch, okay, if you can't get a whole number for x. Hopefully there won't be too many of those, because there have been some problems in the past when it doesn't come out exact, and I noticed that this latest version of StatCrunch has that capability of accepting fractional values. And I have asked the publisher to change the problem, the numeric values, so that it always comes out to be a whole number here. And they have changed some of the homework problems. So hopefully the ones in my stat lab won't be a problem. Okay? But if they are, send them my way, and then I'll request that they change the algorithm, because that's what they do. It's an algorithm that generates the values, to always be that this comes out a whole number. Okay? Okay, so let's take a look at this problem. An oceanographer claims that the mean dive depth of a North Atlantic right whale is 115 meters. A random sample of 34 dive depths has a mean of 121.2 meters and a standard deviation of 24.2 meters. Is there enough evidence to reject the claim at alpha equal 0.1? Okay, so if this were on a test and all mixed up, you would want to first identify the parameter. So here's the clue, right? It's a claim about a mean, so my parameter is mu. So my options for tests are either the z-test or the t-test. So reading this problem, I'm not told to assume the population standard deviation is any particular value. Instead, I'm given the sample standard deviation. So this is going to be a t-test. Okay, sound good? Okay, so I'm going to write first the claim as a mathematical statement. Okay, so that's going to be mu is equal to 115. Okay, so this is the claim. So will this be the null or the alternative? It's going to be the null. So this forces the alternative to be not equal to 115. Okay, so this is a two-tailed test. Okay, so first I want to calculate the standardized test statistic. Okay, so that's x bar minus the claimed parameter over s over the square root of n. Okay, so reading the problem for n is equal to 34. We had a mean of 121.2 and a standard deviation of 24.2. So to do this by hand, I would just plug and chug. Okay, I've got 121.2 minus 115 over 24.2 over the square root of 34. Okay, so again, we're looking at the difference here in the numerator. Okay, we did get a sample value that was not equal to 115, but what we want to know is this difference statistically significant? Okay, so putting this in the calculator, okay, move that over a little bit. Okay, I'm going to put parentheses in the numerator and parentheses in the denominator, because this thing can't read my mind, like so. Okay, do you get a value of 1.494-ish? Okay, so it's about 1.494. Okay, so now we want to find the critical values. There's going to be two because this is a two-tailed test. Okay, so critical values I need my level of significance, and what is that for this problem? 0.1? 0.10? Okay, so I'm going to draw something bell-shaped, put 0 in the middle, and shade my two areas of rejection. Now, because it's a two-tail test, I need to divide alpha in two. So how much area is in one tail by itself? 0.05, right? So 0.05 in each tail, like so. Okay, so I'll have two t-values here that are the critical values, but they're going to be opposite in sign. So to use the table, I need the degrees of freedom. If n was 34, then the degrees of freedom will be 33. Okay, so looking at my t-distribution, I want to first read down to 33, okay, and then I want to read over to the column that has 0.05 area in one tail, or 0.1 between two tails. Okay, so how about this one right here? See 0.05 in one tail, and then together 0.1 for the two tails. Okay, so I'm going to read over and then down. Okay, do you get 1.692? Okay, so the table only gives the positive one. So I have 1.692. And then I also have a negative critical value by symmetry. It's negative 1.692. When we get to hypothesis test about a standard deviation or variance, we're going to go back to that chi-square table, and we'll have to find two critical values because they will not be symmetric. Okay. Okay, so at this point in time, what will be our decision? Where does our test statistic lie with respect to the critical values? It lies in between, right? My test statistic is in the fail to reject region. Okay, you see that? 1.49 is less than 1.692. Okay. So the decision right now will be to fail to reject the claim, and that will be the decision when we're done, too. Okay, so if I'm failing to reject the null, am I supporting the claim in this problem? Yes, because we're keeping the null, and in this case the null is the claim. There is enough evidence to support, what is this, an oceanographer? Okay, forgot what this was about. There is enough evidence to support the oceanographer's claim that the mean dive depth of a North Atlantic right whale is 115 meters. Okay. Maybe not for the left whale. So it's North Atlantic right whale. But it's not capitalized, so I don't know what that means. But that's okay. I teach math. Right? Okay, so the decision is to fail to reject the null, and we're supporting the oceanographer's claim. Now let's go over, if you have a newer TI, where'd my calculator go? We can get this critical value by using the inverse T. Now not all of you will have a newer calculator, but just in case you do, this is what you'd want to do. Okay. So to get the critical value using the TI 84, very similar to that process I went over to get the critical value using the calculator for the Z distribution, it's expecting a cumulative area as its input. So I can do this two ways. I could find the lower one, first. Okay, so by using inverse T, it's in your distribution menu in the calculator of 0.05. Okay, Or I can also use my inverse t and find the upper one. But if you find one, you have them both because of symmetry. Okay, so for this one, using the upper one, I need a cumulative area. I don't want to put in 0.05. What would be my cumulative area? 0.95. Okay. Okay, so if you have a newer TI, okay, go to distribution and see here, well, it's capitalized with the T. Inverse T. Okay, some of you may have it, some of you may not. If you don't have it, you can also use StatCrunch, the calculator, the T calculator in StatCrunch. Okay? Or you can just use the table like I did. Okay, so it's expecting a cumulative area. So I can put in 0.05. And then it needs the degrees of freedom. Okay, and then paste. Okay, so is that approximately what we got using the table for that negative critical value? Yeah. Okay, if I wanted to find the upper critical value, I could put an area of 0.95. And it should give the positive value. Okay. Or you could just find one and just remember this is symmetric. Okay, so we need to find the p-value. Now we're not going to use the table to do this. Okay, so the p-value is the probability of getting a test statistic at least as extreme as the one obtained by the sample. Okay, so I'm going to get this in the calculator. Okay, so using the t-test in the TI 84 or 83. Okay. So I'm going to go to Stat, right arrow over to Tests. Okay, the z-test is for section 7.2. We want the t-test, test for the mean when sigma is unknown. Okay, I could either have the raw data in a list, all 34 values, but I have the summary statistics, so I'm going to leave that highlighted. And I'm going to put in the parameter from the null, which is 115. Okay, my sample mean in this problem was 121.2. Sample standard deviation is 24.2. And my sample size was 34. And then I can overwrite the direction of the alternative. Okay, this was a two-tailed test. And then calculate. Okay, so is this test statistic of 1.493 and so on the same that we got by hand? Yes. Okay, so you could use the t-test to do this in the calculator. That's fine. Now, because this is a two-tailed test, the calculator will double the p-value for you. So the output gives the correct p-value. Okay, when you put in the right alternative, it doubles it. Okay, again, the table is limited. We'd only be able to get a range of values for the p-value. So always use technology to find the p-value. Okay. Okay, so the p-value in this case is 0.1447. Okay, so let's compare the p-value. Oops. Let's compare the p-value to alpha. Okay, so my p-value is 0.1447. Alpha was 0.1. Okay, is this p-value less than or equal to alpha, or is it greater than? It's greater than. So in this case, we fail to reject the null. Okay, so if we look back at our critical value in our test statistic, that should make sense. Okay? The p-value corresponds to the area from your test statistic. Okay, and this way, and then we would double it for a two-tailed test. So clearly that area is greater than half of alpha, which would be greater than double alpha. Okay? We saw that we would fail to reject here. When we compare the p-value to our level of significance, we know that we're going to fail to reject the null. Okay? Okay, so we would say there is sufficient evidence. I can't write very fast. To support the oceanographers, I don't know if that's spelled right, claim that the mean, what is this? Dive depth, sorry, is equal to 115 meters, okay, for the North Atlantic right whale. Okay, not to be confused with the North Atlantic left whale. Just kidding. Okay, so what type of error may have occurred? A type 2 error. Okay, so since the decision is to fail to reject the null, a type 2 error may have occurred. In other words, we could have failed to reject the null when the null is really false. Okay, but again, that's not an intentional error, and it doesn't mean that it absolutely did occur. Okay, we set alpha so that it's not likely to have occurred. Okay. Okay, last but not least, let's look at the corresponding confidence interval. Since alpha was equal to 0.1, we would be finding a 90% confidence interval. Okay, so again, I'm going to use my t-interval in the calculator. Okay, so I'm going to press on stat, right arrow over to test, and then scroll down to t-interval. Okay, and it's really nice. It kept the information from the hypothesis test, but I want to change my level of significance to 0.9. Okay, so if alpha is 0.1, the confidence interval is 0.9. If alpha is 0.05, the confidence interval is 0.95. Okay, so our confidence interval goes from 114.18 up to 128.22. Now, did this confidence interval, does it contain 115? Yes, it contains the equality from the null, which supported the oceanographer's claim. But this also gives me a sense of direction here. Okay, it looks like on average they might also be diving a little bit deeper than that. Okay, because some of this confidence interval is above 115. Okay, so as a researcher, this would give you more information rather than just equals versus not equals. Okay? Does that sound good?